Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. Oh, question. Question from the chat. Let's see. So in general and for the project, is a pretty solution. Yeah, good question. So the question here is about mesh convergence tests. So typically, when you do a mesh convergence test, you do it on one specific output. So the question is, do you do a mesh convergence test for each solution that you're displaying, or is it you just do one type? So usually, you just do a mesh convergence test for one solution. Usually, it's going to be the solution that's most difficult to converge out of the ones that you were considering. And so for you guys, it's mostly going to be equivalent stress. So equivalent stress is going to be probably the most difficult quantity to converge. Deformation converges pretty quickly most of the time. But so if you can show that if equivalent stress is converging, then the implication is that deformation will converge as well. But if you're reporting different things like, different types of stresses or maybe factors of safety, things like that, you may consider more convergence tests, but usually just one for the most difficult thing. Yeah. Okay. So the plan for today, so we're going to continue on this path of doing kind of theoretical knowledge. So last week we introduced the concept of the direct stiffness method. So we did, we introduced this with springs and we did a couple of examples with that. Today, we're going to expand this method to include different element types. And we're starting with the truss element, the Humboldt truss. And so we will see kind of how that kind of adjusts our method here. And probably what we're going to do, what we're going to end up doing today is we're going to start kind of going into 2D problems as well. All right. So just a reminder, your midterm project is due next week, and so just make sure that you guys are working on that. So I'm not going to assign anything else until the midterm project is due. So make sure that you're getting your simulations in, you're asking your questions, and you start writing your report. So now it's kind of starting to get crunch time. So make sure you're at least getting started. You take advantage of all the office hours I have until the project's due. So I have office hours tomorrow, 5:30 to 6:30, office hours on Thursday, 1 to 2, and then next week as well. So next week I have office hours Monday, 5:30 to 6:30, Wednesday, 5:30 to 6:30, and Thursday, 1 to 2. So make sure you take advantage of all of those, or send me an email if you have questions. Okay. All right. Any questions I can answer before we get started? Okay. All right, so let's go ahead and continue rolling. All right, so the topic for today and for the rest of the week is going to be truss elements. Okay, and of course, we're talking about these within the context of the direct stiffness method. Okay, so just to kind of recap a little bit of what we talked about last week. So, last week we introduced this concept of the direct stiffness method, which was a way for you to kind of see what goes on theoretically when we apply the finite element method to a particular problem. Okay. All right. So in particular, what we went over was that the direct stiffness method consists of 4 steps. Although, for you really only have to worry about the first 3. Okay. So the first step of the direct stiffness method is to write out the element stiffness matrices for all the elements. Okay, so if you recall from last week, we had a bunch of springs. When we did our example problem, we had a network of springs all kind of connected to each other. Bless you. And then for each of these springs, we wrote out its corresponding element stiffness matrix. Okay, and our element stiffness matrix, it contained the physical properties of the element itself, So for the springs, it was pretty straightforward. It was just the spring constant. But also more importantly, it also contained the nodes that that element was attached to. Okay. Okay, and so that's going to be important for step two. So step two of the direct stiffness method is to assemble all of your element stiffness matrices. Okay, and so we call step two assembly. And the whole purpose of the assembly step is to take all of your individual element stiffness matrices and combine it into one, what I call kind of global stiffness system. Okay. And so the whole point of the assembly step was to get a matrix set of equations, a linear system of, X amount of equations for a number of unknowns that we can solve for the deformations at each and every one of the nodes. Okay. And we can only do that if we have just one system that governs the entire, or excuse me, one matrix that kind of governs the entire system. Okay. All right. But that step by itself doesn't give us a system that we could solve. And so in order so that we can solve the system, we have to apply boundary conditions to step two. Okay. So step three is to apply boundary conditions. Okay. So we had two types of boundary conditions. Remember, we had mode type boundary conditions and constraint type boundary conditions, and we treated those a bit differently. Okay. And then step four here is to solve the system. Okay. But for the most part, you're not going to be solving these, problems by hand. All you're really just doing is you're going to be setting up the matrix set of equations, and then you're going to be turning it over to MATLAB or your graphing calculator or Wolfram Alpha to solve it for you. Okay. Okay. So that was our general methodology. Okay. So this is kind of the recipe that we're going to be working with over the next next couple of weeks, right? And so the only thing that is going to change really is that, from here on moving forward, we're going to introduce different element types. And different element types means that the element stiffness matrix is going to change for those element types. Okay. So really the only thing that we're changing in this entire process is step one. Okay. Okay. So that's the main thing that we're going to change. And what you're going to see is that truss elements are really not that different from springs. The only thing that's really different is just that, they have a slightly different element stiffness. Okay. There's going to be a little bit, especially once we get to 2D problems, there's going to be a little bit in terms of, how we apply the boundary conditions and the types of boundary conditions that we'll have. But those are fairly minor. So the main thing is, the different element types are going to have different element stiffness matrices. Okay. But besides that, this entire recipe is going to be the same. Okay. All right. And another thing that you have to kind of account for is that, once you start doing multi-dimensional problems, we're only going to go up to 2D in this class just because beyond that, it kind of gets a little bit kind of just crazy and busy work. For 2D elements, you have to account for that at the element stiffness matrix stage as well. Okay. Okay. So we'll kind of start to introduce the concept of 2D elements today, in terms of what's different, but we'll kind of really start to expand on it on Thursday. Okay? But that's just kind of a recap of what we did last week, just to kind of remind you, because we're going to be just building off this process here. Okay. Any questions on any of this? Okay, good. Okay, so let's start with trusses, and let's start with the element stiffness matrix for a truss element. Okay, so let's start by defining what a truss is. So a truss is a structural element type that is only capable of axial deformations. Okay. So what are axial deformations? Axial deformations means that the deformations are within the same or in the same direction as the main axis of the element itself. Okay. So these elements here are normally fairly slender. Okay. So they're much longer than they are wide. So the main axis of this element is the one that goes kind of down, down the length of the element, just like that. Okay. And so if this truss, what we're saying is that it's only capable of axial deformations, then it's only capable of extension and compression. And so what we say is that, all the deformations are going to be within the same, basically parallel to the element itself. Okay. All right. So what are the physical properties that characterize a truss element? So every truss element is made of a certain material that has a Young's modulus. Okay. And so the Young's modulus, we give it the symbol capital E. Okay. Another thing that we know about truss elements is that they have a cross-sectional area. Okay. So the cross-sectional area is given by A. Okay. So the cross-sectional area is if you kind of slice the element, kind of perpendicular to the axis, that's the area that we're talking about. Okay. Oh, another way that you can say is it's the area of the caps. Okay. Okay. Usually we assume that these truss elements are kind of a uniform area all throughout. And then the last property that we know that's going to be relevant for the truss elements is the length of the element. Okay. Okay. So with that in mind, and knowing that our truss element here can only experience axial deformations, okay, let's form the element stiffness matrix. And so just to kind of refresh your memory, the whole purpose of the element stiffness matrix is to form a relationship between the forces that are being applied at the two ends of the element and the nodal deformation, or the deformation that occur at the ends. Okay, so let me go ahead and draw the truss element again. Okay. And let me label the left and right sides of this element. So we're going to call the left side of the element, we'll call it node 1. Okay. And the right side of the element we'll call node 2. Okay. And so on node 1, we're going to be applying a force there. Okay. So actually, let me do it this way. So the force are going to be applied right at the ends, just like this. Okay, so we have F1. We have F2 being applied on the second end. Okay. And then that's going to cause a resulting deformation. We're going to call it X1 on the left-hand side, and then X2 on the right-hand side. Okay. So our element stiffness matrix here is going to be relating F1 and F2 to X1 and X2. Okay. So in other words, we're going to have a matrix system where we have our element stiffness matrix here, okay, multiplied by our deformation vector, X1, X2 is equal to F1, F2. Okay. Just like we did for the spring. So this thing right here is our element stiffness matrix. Okay. So there's a lengthy kind of derivation for this. It's actually very similar to the springs derivation. So I'll kind of spare you just because I don't want to get to the examples here. But if you notice the truss element here, right? Actually, let me overlay with something familiar. So if I overlay a spring on top of the truss, right, you'll see that the way that we define the nodal forces and the nodal deformations for the truss is exactly the same for how we do for the spring, right? So a spring, we didn't really explicitly say it last week, but a spring also is limited to just axial deformations, right? A spring is only capable of expanding and contracting, and that direction is within the axis of the spring itself, okay? So if we take that analogy, and we kind of remind ourselves, what the element stiffness matrix for a spring look like, right? And so to kind of jog your memory, the element stiffness matrix for spring, we had K minus K minus K and K, okay? Where K was the spring constant for the spring itself, okay? Since our truss has the exact same modes of deformation, right? It should make sense that our truss's element stiffness matrix should look very similar to that of a spring. Okay. And in fact, since there's a common factor of K at every entry of the element stiffness matrix, let me factor that out. Okay. And so if we kind of reform this element stiffness matrix here, if we factor out a k, then all we're left with on the inside is a 1, minus 1, minus 1, and 1. Okay. Okay, so we're looking for something in that form. Okay. And so basically what we're saying is that our truss should have what's called like an equivalent spring constant. And so, there's no such thing for a truss. There's no truss constant, but we should get something that's roughly similar based on the physical properties of the truss element itself. Okay. So let's remind ourselves, what the physical properties of the truss are. Okay. So the physical properties of our truss are Young's modulus, its cross-sectional area, and its length. Okay. Let me go ahead and write the typical units for all of these. Okay. So the units for the Young's modulus is usually in Pascal, so that is a Newton per meter square. Okay. The SI unit for area here is just going to be meter square. And then the SI unit for length is just meter. Okay. If we compare that to the SI units for spring constant, okay, the SI units for spring constant is just Newton per meter, right? So spring constant, it expresses how much force the spring will exert based on how much you deform it. Okay? And so the question is, can we combine all three of these properties here, E, A, and L, so that it has the same units as the spring constant? Okay? And the answer is yes, because all we have here are just newtons and meters. So it's just kind of finding a combination of all those things. Okay. Okay. And so if we take, so let's say we take the Young's modulus, we multiply it by the area, and then we divide by the length. Okay. Let's check the units for this. And so if we take Young's modulus, which is Newton per meter square, multiplied by area is meter square, divided by meters. Okay. And so if we do a little bit of stoichiometry here, we cancel the units. We get Newton per meter. Okay. So this quantity right here, EA over L, which incorporates all the physical properties of the truss element itself, has the same units as the spring constant. Okay. And so based on this fact, and based on the fact that, again, our truss element here has basically the same deformation modes as our spring, we can write out the element stiffness matrix for the truss element itself. Okay. And so the element stiffness matrix for a truss is, we have matrix 1, minus 1, minus 1, and 1. Okay. And then to this matrix, we're going to multiply it by the Young's modulus of the element multiplied by its cross-sectional area divided by L. Okay. So again, it looks very similar to a spring element stiffness matrix, except instead of the spring constant, we have EA divided by L. Okay. All right. Any questions on that? Okay. All right, so let's do a quick example to kind of show you this in practice. Okay, so let's consider the following three bar assembly. By the way, sometimes you're going to see problems use the term bar. Bar is the same thing as truss. Okay? So those two terms are interchangeable. Okay, so bar, same thing as a truss. Okay, so let me go ahead and draw it out for you. So this is a pretty simple geometry. So we just have three bars kind of connected end to end. So we have element A, element B, and element C. Okay. Three bars connected. Each of the bars are going to have the same length. And so we're going to assume that each length here is 30 inches. Okay. And so the total length of the entire assembly here is 90 inches. Okay. Okay. And then we need properties as well. So properties of the elements. Elements A and B are identical, so they're going to have the same Young's modulus in the same area. So elements A and B are going to have a Young's modulus of 30 times 10 to the 6 psi. And they're going to have a cross-sectional area of 1 inch square. Okay. Whereas element C here is going to have slightly different properties. Okay. So for element C is going to have a Young's modulus of 15 times 10 to the 6 psi. And the cross-sectional area is going to be 4 inch squared. Okay. Oh, we should label the nodes. So we're going to say the node that's attached to the left wall is going to be node 1. Second node here is going to be in between A and B. Node 3 is going to be in between nodes or elements B and C. And node 4 is going to be attached to the wall. Okay. Okay. We also need a force. This assembly here wouldn't be doing anything if we didn't have a force. So let's assume that we have a force applied on node 2. And our force being applied on node 2 is going to be 3,000 pounds. All right. So that's everything that's given in the problem. And so what we want to do here is we want to compute the deformations of nodes 1, 2, 3, and 4. So we want to compute Okay, so we basically are going to be using our direct stiffness method to compute the deformations of all the nodes in this assembly. Okay, so we're going to go through the entire direct stiffness method, element stiffness matrices, assembly, boundary conditions, and then we'll get mathematical result, of course. All right, any questions on the setup for the problem? Okay, so let's go ahead and solve this. And so let me go ahead and let's write out the steps for the direct stiffness method again. Okay. So first step of the direct stiffness method is to write out the element stiffness matrices for all the elements. Okay. All right. So the element stiffness matrix for a truss, remember, is we multiply the cross-sectional area by the Young's modulus divided by L, and we multiply by the matrix 1, minus 1, minus 1, and 1. Okay. So remember, elements A and B are identical to each other, so they're going to have the exact same factor out in front. Okay, so let's go ahead and just pre-compute that. Okay. So let's compute AE over L for elements A and B. Okay. So we come back up here. So the cross-sectional area for elements A and B is 1 inch squared. Okay. The Young's modulus is 30 times 10 to the 6 psi. And the length, we know from the original problem, is 30 inches. Okay. All right, so we just do some simple arithmetic here. We just, do the division of 30 times 10 to the 6 divided by 30. And so our constant out in front here is 10 to the 6. Okay. Pounds per inch. Okay, so let's go ahead and plug that in and compute the element stiffness matrices for elements A and B. Okay, remember arguably the most important point of this part here is to make sure that you attach the correct nodes to the to that element. Okay. Okay, so let's start with element A. Okay, so element A we have AE over L, which is 10 to the 6 for element A, multiplied by 1, minus 1, minus 1, and 1. Okay. We know from the figure here that element A is connected to nodes 1 and 2. Okay, so this is multiplied by x1, x2. Okay. This is equal to f1 and f2. Okay, and the reason we did it like this is that it's connected to nodes 1 and 2. Okay. So let's do the same thing for element B. So element B, we have the same factor of AE over L in front, and so that's 10 to the 6, multiplied by the matrix 1, minus 1, minus 1, and 1. Okay. Now we need the nodes that are connected to element B, so let's go back up to the figure and see. So based on the figure here, you can see that element B is connected to nodes 2 and 3. So that's x2, x3. And this is equal to f2, f3. Okay, now we have element C. Okay, so for element C, element C has different properties. So we need to compute, a different AE over L factor. Okay. AE divided by L for element C. Okay. Let's go ahead and plug in the numbers for this. And so element C has a cross-sectional area of 4-inch square. Okay. Its Young's modulus is only 15 times 10 to the 6 psi, and the length is 30 inches. Okay. All right. So we have some simple arithmetic here again. So we have 4 times 15, which is 60 times 10 to the 6 up top. And we're dividing that by 30. And so what we get from this is 2 times 10 to the 6 pound per inch. Okay. Okay, and so we can use this number to compute the element stiffness matrix for element B, noting that for element C, noting that element C here is connected to nodes 3 and 4. Okay, so the element stiffness matrix for this is 2 times 10 to the 6 multiplied by 1 minus 1 minus 1 and 1. Okay, multiplied by x3, x4 is equal to F3 and F4. Okay. Okay, and there you have it. That is all of our element stiffness matrices for the 3 elements in our system. All right. Any questions on how we got these results here? Okay, good. All right, so now that we have the element stiffness matrices, the next step is to assemble and so we want to combine all these two things together into one global stiffness system. And so since we have 4 nodes in the system, that means our global stiffness system here is going to have 4 rows and 4 columns. Okay. And so our 4 rows are going to correspond to the 4 deformations. So x1, x2, x3, x4, okay, is equal to f1, f2, f3, f4. Okay. And then the 4 columns, we're going to label it just for convenience as well. So we have x1, x2, x3, x4 column. Okay. All right, so that's our 4x4 system. So the next step here is to take all of our element stiffness matrices and insert them into the proper locations in the global stiffness system. Okay, so let's start with element A. Okay. We know that element A is connected to nodes 1 and 2. And so we're going to block off those areas of the global stiffness system here. Okay. So nodes 1 and 2 are going to be the first 2 rows and the first 2 columns. Okay. So that's going to be this area right here. I'll fill it in a second, but I'm just gonna block off all the areas that we need to. Okay. Okay, next we have element B. So element B is connected to nodes 2 and 3. Okay, so that's second row, second column, third column. So that's this area right here. Okay. And then finally we have element C. Element C we know is nodes 3 and 4. Okay, so that's third row, fourth row, third column, fourth column. So it's this area right here. Okay. So let's add all of our entries in now. Okay. So you're going to come across situations like this where your spring constant or your constant out in front is going to be some very large number, right? And so in this case, our number out in front is 10 to the sixth. Okay. So to save yourself on some writing, what I like to do is I like to factor out any constant term through from the left-hand side. Okay. And so what I did here was I factored out 10 to the sixth from every term inside the matrix. Okay. Just because it's a little bit more convenient than writing 10 to the sixth in every entry in the matrix. So if every term there has that term in common, we just factor it out, and then we just have to worry about kind of the smaller numbers within. Okay. So let's go ahead and start adding the numbers in here. And remember, if we have any overlap just basically means that you add those entries together. Okay. So for element A, now that we've already factored out the 10 to the sixth, we have a 1, minus 1, minus 1, and 1. Okay. Then we add in element B. Element B, we also have a 1, minus 1, minus 1, and 1. Okay. And then element C. Now, element C, you have to be a little bit careful. Remember, element C was different. And so if you look at the factor that's out in front for the element stiffness matrix for element C, you can see is 2 times 10 to the sixth. Okay. And so from this, we're going to add plus 2, minus 2, minus 2, and then positive 2. Okay, so for everything that's overlapped, I'm just going to go ahead and simplify and add those factors together. And so in the second row, second column, we have a 1 plus 1, which is going to be a 2. Okay. And in the third row, third column, we have the intersection of elements B and C. So it's a 1 plus 2, that's going to be equal to 3. All right, and then every other location that we don't have any element stiffness matrix, remember, we fill it in with a 0. Okay. Any questions on how we did the assembly for this problem here? Okay, good. All right, so third step is we need to apply the boundary conditions for this now. Okay, so we have 3 boundary conditions that we need to apply. Okay, so I'll start with node 1. So if we go back up to the figure here, we can see that node 1 is fixed to the wall. Okay. So node 1 here, we're going to apply a fixed support or fixed constraint. Okay. We have a boundary condition that's applied on node 2. And so node 2, we're applying our force on that. Okay. So we have a force of how much force was it? It's 3,000 pounds. Okay. We don't have any boundary condition applied on node 3. So node 3 is kind of free at this point. Okay. But we do have a boundary condition applied on node 4. And so if you go back up to the figure, you can see that node 4 is fixed to the wall. And so that means we're going to apply a fixed boundary condition support on node 4. Okay, so let's go ahead and apply these three boundary conditions to our system. Okay. Let's start with the fixed constraints. Okay. So remember what we do for constraint type boundary conditions is that we replace the entire row with that constraint. Okay. And so let's go ahead and apply the boundary condition on node 1. So node 1, we're going to replace the entire first row with zeros, except for a 1 in the main diagonal. Okay. So our first row there is going to be changed to 1, 0, 0, 0. Okay. And then on the right-hand side for the forcing vector, we're going to apply a 0 here as well. Okay. All right. And so we're going to do the same thing for the last row because node 4 is fixed as well. Okay. So once again, we're going to transform this entire row to zeros and ones. And we're going to put a 1 on the main diagonal. Okay. Remember we talked last week that, when you're applying or when you're choosing a location for the 1 for a fixed constraint, you want to do it on the main diagonal term. So basically on the column that matches your current row. Okay. Okay. So for node 4 right here, that means we're going to put the 1 on the fourth column because it's the fourth row. Okay. So our row is going to be 0, 0, 0, 1. Okay. And then F4 right here, we're just going to put 0. Okay. Okay. So that's boundary conditions 1 and 4. Let's go ahead and apply the load type boundary condition now. So we have a load type boundary condition applied on node 2 with a magnitude of 3,000 pounds. So remember, load type boundary conditions are the easiest, and so all we have to do is just input that force amount onto the right-hand side vector. Okay, so we're gonna replace little f2 in the right-hand side forcing vector with 3,000. All right, and then the last thing we need to do before we solve is to replace little f3. And so we don't have any boundary condition applied on node 3 right there, so we can just turn little f3 into 0. All right, so after all of that work, we end up with the following system here. Okay. And so we can now take the system and solve it in MATLAB. Okay. So you have 4 equations and 4 unknowns up there. So you can use MATLAB to solve this matrix system. And so you plug this into MATLAB, and what you get is x1 is equal to 0 inches. X2 is equal to 0.0018 inches. X3 is 0.0006 inches. Okay. And X4 is fixed to the wall. So X4 is going to be 0 inches. Okay, so those are our four deformations. All right, any questions on how we got these results here? Okay, good. All right, so hopefully that example was also kind of a good refresher for the direct stiffness method. But besides the fact that we're doing trusses instead of springs, that example is not too different from the ones we did last. Okay. All right, so now it's time for something different now. So let's take our 1D problems here and let's take it to the second dimension. Okay. So now let's look at truss and spring problems in 2D. Okay. All right. So what we've gone over so far, it's a nice start, right? And so, you have to start learning, these techniques somewhere. But for the most part, it's not really practical because most practical situations you're going to have deformations and geometries in 2D and 3D. And so, it's important to be able to take the methods that we have and kind of generalize it to multiple dimensions. All right. I don't know if it's the same way now, but I remember when I was in school and I was taking physics classes, and usually whenever you get introduced to a new theory, whether it's forces or momentum or things like that, we always kind of introduce it in 1D. And then when we start to get to multiple dimension problems, the professor's always like, oh yeah, it's just the same thing in multiple dimensions. That's not true at all. So once you start to add multiple dimensions, things get a lot more complicated because there's just a lot more directions and a lot more things to kind of keep in to take into account. And so I'm not going to trivialize this. This is probably going to be the hardest part of this direct stiffness unit, which is how do we take these methods and extend them to 2D? Okay. Okay. So to start, let me say that all the theory and all of the element stiffness matrices that we've developed so far has been assuming a one-dimensional system. Okay. And so what I mean by that is that all the deformations, all the forces, all occur in the same direction. Okay. Okay. And it just so happens that the one direction that we've been considering is the axial direction of our springs or our trusses. Okay, so it's all kind of been it's all kind of been very nicely kind of designed. Okay? But in reality, we have situations where we're going to have deformations that go vertical as well as horizontal itself. Okay. In particular, we're not going to break the assumption of axial deformation. So we're still going to assume that all of our deformations are going to be in line with whatever element that we're considering. Okay. But we are going to start considering the situation now where maybe our elements are tilted. Okay. So maybe they're slanted up in a certain direction, or maybe they're even vertical. Okay. So instead of having a truss that's perfectly horizontal like this, okay, what if we had a truss that was angled up at an angle theta? Okay. Now, how do we approach this type of problem? Okay. Even more challenging is what if we had another element that's attached to the slanted one, right? So what if we had another element, this one, a horizontal one, attached like that? Okay. So how would we handle these situations? How would we, be able to form our stiffness system when our elements are facing different orientations? Okay. So to deal with this, we need to introduce a couple new concepts. Okay. So let's introduce the idea that, we can work in multiple different coordinate systems depending on the orientation of the element itself. Okay. So what I'm referring to here is, let's introduce the concept of a local coordinate system, or basically an x coordinate that's attached to the element's orientation. Okay. Okay, so a local coordinate system is a coordinate system that's attached to an element's orientation. Okay, so traditionally, when we think of a Cartesian coordinate system, we think of, x, y, something like this. Okay, so x is horizontal and y is vertical. Okay, and so far, we've done problems where our trusses and springs align themselves with that x-axis, right? And so if you have a truss like this, or a spring like this, right? They're aligned with the x-axis, and so there's no need for an additional coordinate system because these elements already align themselves with the traditional x1. Okay? But just like the example I did above, what if we had an element that's like this, right? Where it's angled with respect to the horizontal by an angle of theta. Okay. All right. One way that you can kind of interpret this is that, if we started this element from the horizontal x-axis, to obtain this orientation, we had to rotate counterclockwise by an amount of theta. Okay. And so in other words, what we can say is that this theta here represents a rotation angle, right? So an angle in which, we're rotating from the horizontal. Okay. All right. And so the question is, how do we determine the element stiffness matrix for an element like this? Okay. So what if we do this? What if we, draw a second coordinate system that's parallel to the element itself? Okay. So what if I define a new coordinate system, x hat and y hat, that are, align itself with the element? Okay. And so the coordinate system x hat, y hat, okay, this here represents a local coordinate system that's local to the element itself. Okay. So why would we do this? Why is this useful? Right? If you think about how our original element stiffness matrices were defined for our springs and trusses, they were defined with the assumption that the x-axis was parallel to the element itself. Okay. And so if we take this local coordinate system, then what we can do is we can define a local element stiffness matrix, using these local coordinates. Okay. And so we would have A times E divided by L. Okay. So A and E and L, those are all physical properties of the element itself. So those are independent of the coordinate system. So it doesn't matter, if we look at the element like this, or if we rotate our heads 90 degrees, right, it's going to have the same Young's modulus, the same cross-sectional area, the same, okay, so those things are independent. The only difference is now is that the deformations that we're going to measure, x1 and x2, are now going to be in that local coordinate system. So we call it x1 hat, x2 hat is equal to f1 hat f2 hat. Okay. Right. Remember, so the hats there represent a coordinate system that's local to that element. So this looks great, right? And so, if we can just use a local coordinate system, then, there's really nothing for us to change because this element stiffness matrix looks exactly the same. The only thing is that everyone has hats, but, whether you wear a hat or not, you're still the same person. I would hope so. Okay. The problem now becomes that what if you have multiple elements that are in multiple different directions, right? And so let's come back up to this figure that I have up here, right? Very simple figure. We have two elements. One is rotated upwards by an angle theta. The other one is horizontal. I know I kind of drew it poorly, but it's supposed to be a horizontal element. Okay. So we can make a local element stiffness matrix for both of these elements. Okay. The problem is the local coordinate system for each of these elements are different. Okay. Which, by itself is not a bad thing, right? So everyone is kind of free to do their own thing. You can kind of march to the beat of your own drum. But, eventually, we want to solve a finite element problem. And part of that is, we have to assemble all of these into the same system. And if we're going to be assembling these guys into the same system, then they have to be within the same coordinate, they have to follow the same coordinate rules. Okay. And so the issue now becomes, if you have elements that are in different directions, how do you assemble them in a way that is consistent? Okay. So let me say assembly. Okay. So how are we going to solve this problem? So how are we going to basically, kind of, take all the local systems, all the local element stiffness matrices, and get them to all be within the same system. Okay. The answer to this is to do a vector transformation. Okay. Basically, what we're going to do is we're going to take these local element stiffness matrices that were defined locally to the elements and perform a vector transformation and basically redefine this element stiffness matrix into a reference coordinate system. Okay. Okay. And so to accomplish that requires, quite a bit of linear algebra. Or I should say a vector algebra. So we'll start it today. We're going to make full use of the final 10 minutes that we have. But I think we'll probably finish the derivation on Thursday. Does this concept of local coordinate systems and vector transformations and rotations, does this all kind of make sense to you guys? Any questions so far? Okay, good. Okay, so let's start let's start discussing about how we can perform this transformation. Okay. All right, and so to perform this transformation, we kind of have to start with the question of what is a coordinate system, anyway. And so a coordinate system is really just a way to kind of define the physical dimensions of a vector. Okay? Okay. So you can call the same vector, the same vector may have different components in different coordinate systems, even though it's the same vector. Okay. So let me kind of give you an example. So let's say that we have a vector u. Okay. So this is just some kind of generic vector that's in 2D space. Okay. Now, traditionally, if we want to define the components of this vector, okay, we would always define those relative to the coordinate system it's in. And so traditionally, we have a traditional kind of XY Cartesian system. We have an x-axis that goes horizontally, a y-axis that goes vertically. Okay. And so to define the components of this vector, what we can do is we can project this vector onto these respective axes. Okay. So for instance, if we project this vector onto the x-axis, right, we obtain the x component of that vector ux. Okay. And if we project this vector onto the y-axis, we get its y component uy. Okay. And so what we can say is that this u vector is represented by ux, comma, uy. Okay. Or sometimes what you've probably seen in your math classes is that we define this in index notation. Okay. And so what we can say is that this u here is equal to ux multiplied by the unit vector I hat plus uy multiplied by the unit vector in the y direction j hat. Okay, where I hat and j hat are just unit vectors in the x and y directions. So I hat looks like this, and j hat looks like that. Okay. I hat, j hat, unit vectors. Okay. Remember, a unit vector is just simply a vector with length 1. Okay. And I hat and j hat are just special unit vectors that are perpendicular to each other, but go in the x and y directions. Okay. Okay, let me draw that same vector u. Okay. So it's not going to look the same because I'm terrible at drawing, but just imagine that it's the exact same vector. Okay. Okay. So I've drawn an identical vector u. Okay. But instead of defining this vector with respect to the traditional x and y, let's define it in terms of a rotated coordinate system. Okay. And so let me go ahead and use purple here. Okay. And so now I'm going to make an x-axis that is slanted up like this. We'll call this x hat. And then we'll have a slanted y direction y hat. Okay. And what we can say is that this coordinate system is rotated counterclockwise compared to the traditional x and y by an amount theta. Okay. Okay. So same vector u, but different coordinate system x hat and y. Okay. Once again, we can project this vector onto the coordinate axes. Okay. And we can get the components of this vector u x hat and u y hat. Okay. Okay. And so what we can say is that the u vector here has components u x hat and u y hat. Okay. I just realized I fucked up the notation. I do this every year, and I tell myself I'm not going to do it, but I use hats too much. I'm just a happy person. Okay. And so same thing as before. So we can write this in kind of unit vector notation here. And so this is equal to u x hat. How am I going to differentiate this? I'll call it I hat underline. Okay. Plus u y hat times j hat underline. Okay. Where I hat underline and j hat underline are unit vectors in the x hat and y hat directions. Okay. We have two different ways of defining this vector, right? And so, probably you can tell from this image right here that ux is not the same as ux hat, right? And so they both represent, the components of this vector, but they're relative to different coordinate systems. Okay, so depending on the coordinate system that you're defining it by, the components of the vector are going to change. Okay, but the vector itself is still the same, right? So the u vector is the same. So even though the individual components are different, overall we have the same vector. Okay. And so it's like the same thing, if you have a cousin and half your family calls him Bill, the other half of the family calls him Bob, he's still the same guy, right? It's just you call them by different names. And so this is kind of the exact same scenario. And so what we can do is, so if we say that the u vector is the same, we can take both of these unit vector expressions and set them equal to each other. Okay. So even though ux and ux hat are not equal to each other individually, overall their vectors are the same. Okay. And so what I'll end with today is to say that, ux multiplied by I hat plus uy multiplied by j hat is equal to ux hat multiplied by I hat underline plus uy hat multiplied by j hat underline. All right, and so we'll pick this up on Thursday, and so we'll basically work with this expression and work with the fact that, we know the rotation angles, we know theta. We're going to do a little bit of trigonometry to kind of form this relationship and turn it into our vector transform. Okay. All right, any questions on this before we finish up for today? Okay, all right, so that's all I got for you guys today, and so thank you guys for coming. Hope you guys have a good rest of your day. Remember to start working on the project if you haven't started working on it yet. And so, I haven't gotten that many questions, so I'm starting to get a little concerned. So make sure you start, ask your questions, and just so it's not a big rush next week. So thank you guys. See you guys on Thursday. Yeah.
So for our objective, we code the objective.
Exactly.
So I can be, but I was thinking a scenario, the appraisal It's drawing.
Yeah, yeah, yeah.
In the grip handle.
Yeah.
So can I do something like that?
Yeah, oh, that's
Now
perfect.
material into my steel or brass.
That's perfect. That's exactly what I'm looking for. So something, you know, you look at the geometry, you think of, you know, how could this be used in practice? And you kind of think of a scenario like that.
Okay.
And that scenario is going to inform your boundary forces that you apply, direction.
And like, what, I'm kind of confused when you displace the.
Most of the time, you're just gonna use a fixed support and then you're gonna apply forces. So that's generally how we think.
And refinement is usually used like the thing stress to the highest, like that one problem with the plate.
Exactly.
The plate.
Yeah.
Okay.
Yeah. Right.
Is that a quick question about
Yeah.
the project?
Sure.
Just wanted to ask like how creative we can get with it, or do you want it to still kind of be, it's semi-professional or whatever?
So in the past, I've had people, you know, say like, what if this is made of like radium? So
Right,
you can be creative.
Okay.
I love that, but
Okay.
but nothing too like too crazy.
Right.
If you're not sure, you can always ask.
Okay.
And then you know, tell you yes, but you know, for the most part, you know, like you can't use the handle, you know, you can't say this handle is bloody, so I don't want that. So you can still use the handle of the hand.
Okay. That's funny. You called me out there. Cause like, I was like thinking, I'm like in a post-apocalyptic environment.
Yeah.
That's,
I thought about that last year, but last year I had a teller, and so what if I tell her to be funded down? No.
Okay.
Let's not go there.
Thank you for answering.
But another question
Yeah.
about the exam, so when it comes to the exam, we're doing a handle, right? And just wondering, there is pressure on the thing, right?
Yeah,
Okay, and,
you got for the project.
yeah, for probably, and just wondering, so will the pressure be more on the bottom of the thing? Because it's like being pushed, being pulled down also.
Most likely, yeah, so most likely, you know, you're gonna handle something, either pull something or you lift it up.
Right.
So most times the force are in the.
So it's pretty much on those axes, like, the, I don't know, this axis to like.
Yes, yeah. Yeah, depends on how you load it, but I can see it being loaded. Traditionally, you know, you pull a handle like this,
Yeah.
but you can also, you know, use the handle kind of pull, shear and down.
Gotcha. And usually there's more pressure, like, I don't know, if it's like, but there's more pressure down here because like the.
Exactly.
I think I said it again, I'm just, I don't know, why I said it again.
It helps talk through it.
Yeah. Got it. Thank you.
Yep. Question in the chat, let's see. Oh, thank you, you're welcome. All right, see you guys.